Hello, welcome everyone. This is Fluid Machinery and our next online lecture, which will be about fans, so ventilators. So when we speak about fans, we can make use of a lot of things we've already learned about pumps. For instance, we can speak about radial fans, as you can see. And if you have a look at the performance curve of such a fan, you will see that it's very similar to the ones we've already dealt with in the case of pumps. Okay, so this could be, based on its shape, the performance curve of a radial pump. You can also see that these can be ran either at 50 or 60 Hertz. So for example, frequency converter is also a very often used equipment to control them. And for example, the affinity laws we've already learned can be also applied for fans. We can also have axial fans. Okay, so this is again something that looks very similar to pumps, axial pumps. And as you see, the performance curve of an axial machine is quite different from the radial ones. So I would like to explain now what the difference is in the performance curves of an axial and a radial machine. Okay, so what I'm explaining now applies both for fans and pumps. Okay, what you see here is three coordinate systems. In each x-axis we have the flow rate. It's actually a slightly different flow rate. So what we do is that we take the optimal point. So all the quantities coming with an asterisk sign are the actual quantities, so in this case flow rate, divided by the flow rate of the optimal point. So best efficiency point, okay? So what happens is that you take either the flow rate or the head or the power or the efficiency. You take the best efficiency point and then you divide it. Which means that no matter what your machine's performance curve actually looks like, it will pass through the 1, 1 point. So this point. Okay, so no matter if it's a radial or axial, a mixed pump, whether it's a small one or it's a large one, if you use this coordinate system, then all the curves will pass through the 1, 1 point. Okay, this is only needed to make a sensible comparison between the shapes of the curves. So we have three curves here. R stands for radial. Okay, so this would be a radial machine, which looks like this. M stands for mixed. It's neither radial nor axial. It's somewhere in between. It would look something like this. So for example, here the flow is in this direction. Okay, so you see that when it goes through the impeller, which is the yellow region, it's neither radial nor axial. It's something in between. Or it can be also an axial machine, okay? And then the color coding is important. So in each figure, the red corresponds to these machines, the magenta, not this funny blue color corresponds to the axial, and that black one is the mixed impeller. If you have a look at the head curve, so the pressure difference of a radial machine, and if you start off with small flow rates, first it's increasing, and then it will decrease, whereas for a purely axial machine, it will decrease all the way around. So the highest pressure difference is when you close the pressure side valve, and the smallest pressure difference is at the highest flow rates. In terms of input power, I'm sorry, this is in. So for the input power, if you take a radial machine, the power will increase as you increase the flow rate, and the smallest required power is at small flow rates. Now, if you have a look at an axial machine, but you will see that the power curve is decreasing, so the smallest inlet power need is at the highest flow rates. So this means that when you start your machine, so when you switch it on, in order to protect the driving electric motor, you have to start a radial machine with closed valve. I will write it here for you. So this is closed valve. That means that when you start off on your pump, the flow rate will be 0. Just a second. So when you start a radial machine, you close the pressure side valve, which means that when you switch it on, the flow rate will be 0. And then once the system is up and running, you slowly open the valve and reach the desired operating point. Whereas if you have an axial machine, then the smallest power input is at large flow rates. So the way you start these machines is with an open valve. Okay, so you fully open the pressure side valve to provide as large flow rate as possible. Open valve, and then in order to reach the desired operating point, you close your valve. Okay, so this is an important difference. Now, if you have a look at the efficiency, so this is just good efficiency in Hungarian. So if you have a look at the efficiency curve, you see the following. So let's ask the following question. Let's say that this is 90% efficiency, okay? And then you ask yourself, what is the flow rate region in which my machine can run with at least 90% efficiency? It's fine if it's higher, but I require a minimum of 90% efficiency, and I want to see what the flow rate range is where I can fulfill this requirement. Now, if you take a radial machine, then everything between these two intersection points has a higher efficiency than 90%. So for a radial machine, this range is relatively wide. Okay, so that means that you can change the flow rate in a wide range and still get good efficiency. Whereas in the case of an axial machine, this range is much more narrow, much narrower. Okay, so this is again a big difference, that for a radial machine, the flow rate range corresponding to a prescribed minimum efficiency is much wider than the same for an axial machine. Good. Okay, so now let's speak about fans. So all that I've explained so far applied both for fans and pumps, but now we will work specifically with fans. So first of all, as we've already learned in the beginning of the semester, if the pressure rise is less than approximately 20 or 30% of the suction side pressure, then density can be assumed to 0. Okay, so this is very important, that by definition we call a machine a fan or a ventilator if the pressure ratio is less than approximately 1.3, and that means that the density of air that the ventilator, the fan, conveys can be assumed to be constant, so essentially it behaves the same as a pump in terms of velocity triangles and Euler's turbine equation. Now there is a difference, however, that the change in the potential energy is always negligible. Okay, so the specific work for a fan is given by pascals usually, so that's the usual unit. Okay, in pumps this was meters of water column and we called it head, but here it's pascals, which is essentially joule over cubic meter, so the energy increase of the gas of 1 cubic meter. Okay, and then the total pressure rises is the pressure and kinetic energy and geodetic height, so the Bernoulli enthalpy change between the pressure side and the suction side. But as I said, the change in the potential energy is always negligible. That is, you can get rid of these two terms. This is simply because the density is so low. Okay, the velocities can be high, but the densities are so low, and also the height differences are so low that you can happily omit them. So this is the total pressure rise. The T stands for total pressure. Okay. Now we've also learned Euler's pump equation. So in the ideal case, this is how you compute it. Again, if you have pre-rotation free flow, then this term can be cancelled. Okay, and then if you multiply the ideal value with the hydraulic efficiency, then you will get the same thing. So let me explain this. The Euler's turbine equation, so this equation gives you the total pressure difference in terms of the internal of the pump, of the fan or the pump. So this will include revolution number, impeller diameter, blade angles, etc. Okay, so this equation is concerned with the internal structure of the machine, the size, the revolution number, the number of blades, etc. Whereas the other equation handles the machine as a black box. Okay, so it says that I have a black box, air flows through this black box, and I simply take the energy difference between the pressure side and the suction side. Okay, so this is the interpretation of these two equations. Besides total pressure rise, we often use something we call static pressure. Okay, so consider this figure. As you see, this fan is sucking air from the ambient. Okay, and then there is a pipeline, and the whole thing goes into the building. So very often the kinetic energy, so this term, which is essentially the kinetic energy of the air when it's entering the pressure side room or hall or whatever you're conveying the air to, this is lost. Okay, so at the exit of the, for example, at the air ventilation duct, at the cross section where the duct, the pipe enters the room or your commercial center or sport hall, whatever your air condition, wherever you want to put fresh air into, it has kinetic energy, but this kinetic energy, rho over 2cp squared, will be lost because it's dissipated by eddies and turbulence. Okay, so very often we also use static pressure difference, which is by definition the total pressure difference minus the exit kinetic energy. And if you rewrite this equation, you will see that it's the pressure side static pressure minus the total pressure of the suction side. Now, if there is no significant pressure loss in the suction side, like for example here, then this second term is nothing else but the ambient pressure, okay? Because the inlet is without any loss. I will explain this concept in the next slide in more details. Now, the important bit is that by definition, the static pressure rise, the static pressure difference, is the difference between the static pressures at the pressure side volume minus the suction side volume, which is very often the ambient pressure. Okay, so the pressure difference of the ambient and pressure side static pressure. Okay, good. Now, let's see how this pressure difference looks like. I'm sorry about, I left here the Hungarian. So this is pressure distribution, okay? I'm sorry about it. Distribution. It's not really nice, my handwriting. Pressure distribution. Okay. Before we deal with the graph, so let's let's have a look at this equation. In general, we very often say that the total pressure is the static pressure plus the kinetic term, and this kinetic term is very often called dynamic pressure. Okay, so when I speak about dynamic pressure, I think of the kinetic term, and when I say static pressure, I speak about the pressure that you can actually measure. But this should be familiar. You should be familiar with this concept from fluid mechanics. Okay, so this is our fan. This is the suction side. This is the pressure side. And on the pressure side, we have a pipeline. And then somewhere here you have the room which you are air conditioning, ventilating. Okay, it has P out pressure, and in the suction side you have P inward, so ambient pressure. So let's have a look first at the total pressure. So don't forget that total pressure is nothing else but energy. Energy of 1 cubic meter of gas. So if you have losses, then total pressure decreases. If you have a machine that's putting specific energy into the gas, then total pressure will increase. Okay, so we are starting off somewhere far away from the fan, and as the gas approaches the fan, it accelerates up to the suction side. If it's accelerating but the total pressure is constant, then the static pressure will drop, and the difference in between will be the dynamic pressure. So you will measure a slight depression at the lower pressure at the suction side of a fan. Then we increase the energy, we increase the total pressure by the machine, and at the pressure side you have this total pressure again. The difference between the total pressure and the static pressure is the dynamic pressure. Then in the pipeline you'll have losses. If you have losses, then the total pressure decreases. Okay, and this is your total pressure loss. Now, a few weeks ago we dealt with how to compute the pressure loss in pipelines. So this pressure loss here is exactly, if it's just a straight pipe, this is exactly the lambda L over D rho over 2 Vp pressure side velocity squared. Okay, obviously if you have more elements, you'll have bands and elbows and valves, etc., then the pressure loss must be computed differently, but this is the very same pressure loss that we have learned a couple of weeks ago. Now when you enter the exit the pipe, so this is for instance your office, what you need to know is that at this point the static pressure is exactly the outlet pressure, okay, but you still have the kinetic energy term, and this kinetic energy term is lost because of turbulence and eddies. So in the room far away from the exit from the duct, the static pressure and dynamic pressure is the same because the fluid is at rest. Okay, so this is how it looks like, and let's have a look at the same figure in the case of another very common example, when the suction side static pressure and the pressure side static pressure is the same essentially. Okay, so for example, imagine a large office room. Okay, the windows are open, so that means that both in the office and outside you have the same static pressure, so the static pressure difference is 0 in this case. And the very same distribution looks like this. Again, you have the dynamic pressure in between the static and the total pressure. Okay, so it's pretty much the same, but it's another very common example. So for this fan, the static pressure difference is 0 because you have the same start and ending static pressure, but the total pressure difference is this quantity here. Okay, so it's very important that you get familiar with all these concepts, that static pressure difference, total pressure difference, and how they behave in different cases. Next, I would like to speak a bit about guide vanes. Very often in axial machines we use guide vanes, and I will explain the guide vanes behind the impeller. So basically, this is your impeller here, this element. This is rotating, but this one, the guide vanes are standing. Okay, so they are not rotating. Standing. I'm sorry for my handwriting, standing. And I will explain now why these are used. So let's go back to the velocity triangles, which we have already done. So have a look at this figure. We have an axial machine and we have plotted here the velocity triangles and at a smaller and at a larger radius. Okay, so the small one is the blue one, the red one is the larger one. So we have the axial velocity, we have the circumferential velocity, which is again large. The red one is larger because it's at a larger radius. So u is essentially r times omega. So the larger the radius is, the larger the u is, and then the relative velocity connects them. So this is the inlet velocity triangle. If it's pre-rotation free, then this is 90 degrees here. At the outlet, however, you have a circumferential velocity component of the absolute velocity, c2u. Okay? So what we need to see here is that the axial velocity is the same because of continuity reasons, as I've already explained earlier. But we also have a circumferential velocity component which makes the flow progress in a spiral-like way in the exit duct. And this term will be dissipated later. So what we want to do essentially, this is the guide vane here. This is the guide vane. So what it does, it gets rid of this C2U by changing the direction of the outlet flow. So this C2 here is this C2 here. So it's very simple. All what I do is that I make it purely axial again. Okay? Now it doesn't seem to be a big thing, but it is. Because if you have a look at this figure, what we basically did, we turned C2U into pressure, okay? So you can write a Bernoulli equation through the guide vanes because there is neither energy input nor losses. So you can use the Bernoulli equation. And what you see is that after the axial impeller, you have these quantities. So the pressure is P2, and then you have the kinetic energy. I should write here C2 squared, but C2 squared is C2U squared plus C axial squared. So this is the absolute outlet velocity at the outlet of the impeller. After the guide vane, I have only this term here, the axial velocity. So if there are no losses, ideally, this whole term was turned into a pressure increase. At the end of the day, behind the guide vane, the pressure will be larger than the pressure was after the impeller. So what you do basically with the guide vanes is that you increase the pressure rise of the ventilator. So that means that your efficiency is better. Okay? Without the guide vanes, I would have this P2 after the fan, and this C2U squared term would be simply dissipated. Okay? Finally, I would like to speak a bit about noise. Noise of ventilators and fans is just as important as cavitation in the case of pumps. Okay, so nowadays it's extremely important to build silent ventilators, or if it's not silent, then it needs to be very accurately measured what the sound load caused by the fan is. It's very simple. If you have a desktop computer, you don't want to hear the fan running, okay, because it will disturb your learning or whatever you're doing on your laptop or desktop PC. If there is an office in which people are trying to work, it's never used if you can, it's not good if you can hear that the ventilator is running and it adds an extra noise level. Okay, so for noise measurement, we usually use the so-called sound pressure level, SWL, which is basically the acoustic power level, and we use a logarithmic measure. Okay, this is very important. So by definition, you divide the power, the acoustic power, by a reference value, which happens to be 10 to the minus 12 watts. And then you take the 10 base logarithm of it and multiply by 10. The reason we need to do this, because strangely, the human ear also works on a logarithmic level. Okay, so that simply means that you can hear sounds which, in terms of power or sound pressure level, vary on a large scale. I will give you an example. We also very often use something called sound pressure level, which essentially the very same equation, just with pressure squared. Okay, it's not really important now why the pressure is squared. I will explain this a couple of weeks later when I'm speaking about Aliyev's principle and water hammer problem. So for the time being, just believe me that it makes sense to define the sound pressure level with pressure squared. So be careful. This is large P, capital, and this is power. Lowercase p stands for pressure. And then the definition is this, and then the reference pressure is 10 to the minus 5th pascals. Okay, so how do we use these equations? You can make a very simple calculation. So let's assume that the power is 10 to the minus 3rd watts. Okay, now be careful, this is acoustic power. So this is not shaft power whatsoever, this is the acoustic power emitted by the machine. So if this is 10 to the minus 3rd, P node is 10 to the minus. So this is our power level. P node is 10 to the minus 12. Okay. So altogether, this is 10 to the 9th. So then the 10 base logarithm of 10 to the 9th is 9. And then you multiply by 10 and then you get 90. Okay. If you do the same calculation with 0.002 watts, then you'll get 93 decibels. And then the rest is here. What you have to see here is the following. If you increase the power 10 times the previous one, so each time you make the power 10 times bigger, so you're not adding 10 watts, you make it 10 times bigger, you multiply it by 10, then you'll get an extra 10 decibels in the acoustic power level. If you happen to double the power, so if you double it, you will get an extra 3 decibels. Okay. Now, very often we are using something we call an A-weighted sound power level. This is also important. This A-weighted simply means that the different frequency so the noise has different frequency contents. That is, for example, if you take the noise of a car, then you have low frequency components and high frequency components and middle frequency components. Now, not all of these frequencies can be heard. Okay, so the A weighting is simply emphasizing those frequency ranges, that frequency range, for which the human ear is sensitive. Okay, and then we denote it by LVA. Okay, you can read more about on Wikipedia about this. Okay, so what you need to know then is that approximately here is how it changes. So in a recording studio where you have extremely low noise, you have about 20 decibels of sound power level. In a quiet office, you have about 50 decibels. In a crowded subway station, you have 100 decibels. If you are working with a chainsaw, then you have 120 decibels. And for example, an airplane jet takeoff from 25 meters will be 150 decibels. The pain threshold, the pain threshold is somewhere here. Okay, and also somewhere here you have to think about using some kind of protection. Okay, so there are regulations, protection, ear protection, what I mean. I've also had a look at a couple of commercial products, okay, just randomly. Very often they provide these numbers. So for example, this chainsaw has a sound power level of 116 decibels, okay, and the pressure level is actually 103 decibels. This molar has a 96 decibel of sound pressure level, A-weighted again, and this high pressure electric sprayer has a sound pressure level of 102 decibels. Okay, good. So about this section of the material, we are adding a separate chapter in the lecture notes. So if you will have a look at the lecture notes, you'll see there is no chapter called fans. That's something we are working on at the moment, but what we are doing now is we are adding problems with which you can practice. So the material itself is whatever I'm showing in this video, nothing less, nothing more. Okay, in the lecture notes you will not find it yet. Later in the semester we will add this chapter, but you will find the problems corresponding to this chapter. Okay, so thank you for your attention and I will see you next week. Bye bye.